Hi, I'm going to tell you about our recent work on a new facility location formulation of the problem of placing vaccine distribution sites in order to improve the accessibility of vaccines. I'm George, and this is a joint work between a number of researchers from the University of Maryland and University of Virginia. Though vaccines have been developed for COVID-19, we have still been unable to achieve herd immunity due to vaccination hesitancy and a number of other reasons. Throughout the US, most states have a vaccination rate between 60 and 70%, whereas according to the CDC, we need a 94% vaccination rate in order to achieve herd immunity. Some solutions which have been tried include offering lottery tickets to every person who gets vaccinated. This has seen varying effectiveness. Our work focuses on the deployment of mobile vaccination sites. Basically, many states have recently funded a limited number of mobile vaccination sites, and we want to know how to optimally place this around the county or state in order to maximize the accessibility of the vaccines. This is usually formulated as a classical facility location problem, namely the k-Supplier problem. In this problem, we're given as input facility locations F, where we can place the vaccine centers, and client location C, which we can think about as each person's homes. And the goal is to place K facilities in order to minimize the distance from the people's homes to the place facilities. We generalize this problem here. Basically, the idea is that people are not stationary objects. Instead of representing each person by only their home, we represent them by a set, SP, which we can think about as the places people go to throughout a day or a week. And now the goal is to place K facilities such that each person only needs to deviate from their path very little in order to get vaccinated. And we argue that this is a better formulation for our goal, which is accessibility of vaccines. In order to motivate this problem, let's look at an example. Here, the different colors represent different people. The circles represent locations, and these arrows represent where a person goes throughout a day. Also, here in our toy example, k is equal to 1, meaning we can only place one facility. If we use the classical formulation for this example, we would place the facility here, where the star is, because we are only considering the 3 locations on the bottom, which represent the clients' homes. And if you consider that solution and look at this red person, they would need to deviate from their path a considerable amount in order to get vaccinated. In contrast, if we used our formulation, we would place the one facility here in this blue location. And for this, each person only has to deviate from their path very little in order to get vaccinated, and that is clearly desirable. Now that we've motivated our problem, let's look a bit into our results. First, since this is a generalization of the k-Supplier problem, we know it's NP hard. So a natural first approach is to develop approximation algorithms for it. However, as we'll show now, this is essentially impossible. We show that unless P is equal to NP, there can be no approximation algorithm for our problem. Furthermore, that even holds true if we violate the budget K by a log n factor, meaning that we can't get approximation algorithms even if we open K times log n facilities. And the worst case is that this all occurs on the Euclidean line, meaning that even if we assume that we are living in a metric space, we still can't get approximation algorithms. If you get anything out of this slide, you should know that this problem is very hard. But despite these hardness results, we will still give a non-trivial approximation algorithm for our problem. First, let's assume that we know the optimal radius r. This is a safe assumption because we can guess it in polynomial time. Next, let's consider the reverse problem. In the original problem, we were given a budget k on the number of facilities we could place, and we wanted to minimize the radius r. Now, we're given the radius r, and we want to pick the fewest number of facilities in order to cover every single client within a radius r. Now, to imagine this, let's imagine these facilities, and let's draw a ball of radius r around each of them. And we want to pick the fewest number of these in order to cover every single client. If you stare at this problem for long enough, you'll come to the conclusion that this is just a set cover problem, for which there are known approximation algorithms. In particular, the greedy algorithm for set cover is an Hn approximation algorithm, where Hn is the nth harmonic number, and Hn is upper bounded by log n plus 1. Now, if we simply input r star, the optimal radius, into that set cover algorithm, the output will be a set of facilities which covers every single client within radius r star, and furthermore, the size of that facility set will be at most k times Hn, which means that we have a 1 Hn bicriteria approximation algorithm for our problem. Based on the previous hardness result, this is essentially best possible. Now that we have an algorithm for our problem, let's consider a few natural extensions. First, out of all the people in a community, in a county, a state, it's possible that a few of them just live very far away from everyone else. And since our goal here is herd immunity, we can essentially ignore these people. So let's consider the outliers formulation of our problem, where we are only required to serve an alpha fraction of the population, where you can think of alpha as being 0.99. Another natural consideration here is that of fairness. It's well known that COVID-19 disproportionately affects some demographic groups over others. And it's important to make sure that our vaccine distribution doesn't increase that disparity. A final extension, which is especially important here, is capacities. Because these are mobile vaccination sites, they can only carry a limited number of vaccines. As a result, we need to consider the capacitated version of our problem. Luckily, each of these extensions can be solved by considering the corresponding variant of set cover. And these have all been studied before, and order log n approximation algorithms are known for all of them. Hence, by using the same framework we used before for the original problem, we can get 1 order log n approximations for every single one of these extensions. And based on the hardness result that we had earlier, this is optimal up to constant factors. In conclusion, our work here introduces a generalization of the k-Supplier problem, which models mobile populations. What that means is instead of viewing each person as a single point, we view them as a set of points, which can be thought of as where they go throughout a day. And for this problem, we show that it is much harder than the original k-Supplier problem, and we gave a bicriteria approximation algorithm, which matches the lower bound almost exactly. We believe that this introduces an interesting set of new facility location problems for the community to study. Thank you, and I look forward to answering any questions you might have.